in IIT Tirupati. His research expertise additive metallic part development. He has served as a supervisor for many diploma postgraduate students, and he has involved himself in the R&D projects for the government, and he was awarded an Innovation Award at MEDIC 2018, recognizing his contribution to medical device innovation. I welcome you to deliver your speech and make this program a grand success, sir.
Okay, thank you, sir.
Yeah. Thank you very much. Good evening to all of you. First of all, I thank Bethlahem Institute for inviting me for sharing this session on metal additive manufacturing. So I understand that all the most of the participants are faculties from various engineering colleges, and also there are some research scholars. So I believe all are from mechanical background, right? Can somebody confirm?
Yes, sir.
Okay.
Yes,
So my
sir.
voice is audible clearly, right? It is
Yes.
able to.
Yes, it is audible, sir.
Okay. So I'll go to the screen, full screen mode. Yeah. So full screen is seen, right? You are able to see clearly?
Yes, sir, we can able to see.
Okay, thank you. So basically, today's session, I'll be covering mainly about additive manufacturing, focusing mainly on metal additive especially, and its various industrial applications. So before coming to the core topic, I would like to introduce my institute as well. I come from basically CMTI, Central Manufacturing Technology Institute. In short, it is called CMTI. It is basically located in Bangalore. Basically, it is a 63-year-old organization which was established in the year 1962 by Government of India in technical collaboration with OSO, that is a leading R&D center in Czech Republic. So the main aim of CMT is to support Indian industries to excel in the manufacturing sector. That was the main aim. And previously CMT was known as Central Machine Tool Institute. Probably, I believe you might have seen a handbook machine. There is a machine tool design handbook by CMTI. In most of the institutes, it is available, including R&D organizations. If you do not have that copy, do let us know. You can have that in your libraries as well. So basically, CMT was mainly into machine tool development initially. So that is why it is called as Central Machine Tool Institute. Later, it was renamed as Central Manufacturing Technology Institute, because initially we were only focusing on machine tool aspects. Later, we broadened our spectrum of activities to cover other aspects of manufacturing. That's how it was renamed in 1990s as Central Manufacturing Technology Institute. So basically, we comes under Ministry of Heavy Industries, basically, and we have a governing council, and there is a research advisory board also consisting of members from various R&D institutes who help us in our R&D activities. So over the years, if you look at CMTA, we have developed several innovative, solutions, be it special purpose machines, or it could be test rigs, it could be products, it could be inspection solutions. So we have several, developments, more than 500 technologies we have developed over these 6 decades of our existence. And if you look at globally, whenever any new technology is launched, so CMT tried to, adopt that, and we tried to not only adopt, we tried to, help other industries by providing them training on various these new technologies, so that the industries can also be at par with the latest technologies. That is how you can see over the various previous years, you can see. So whenever you can see machine tool technology in 1960s when it was launched, we had the technology here, which we used to train and also use for various industrial solutions. We have used that. Then ANC technology, noise and vibration, fluid power, metrology, then computer, integrated manufacturing, flexible manufacturing solutions, then ultra precision engineering, then later into nanotechnology as well. Nanotechnology, nano product development, machine tool for nano finished products. Then we have nanometrology, we have then additive manufacturing, tooling technologies. So like that, we have, over the years, we, as with the new technologies being introduced globally, we try to catch up and also try to develop in parallel. So many of the solutions what CMTA do is first of its kind in India, if not to the world, first of its kind in India. So we don't try to do something already done by others. So at least in India, whenever we develop any product or machine, we try to see that it is not replicated. So we try to do one of its kind, and that is how CMTA has been working over these years. And if you look at our human resource, we have around 255 permanent manpower, and with if you include our temporary staff, it will be crossing around 400 to 450 will be there. So in that majority, we have around 70 plus scientists, and so majority are technical, and there are around 72 non-technical staff as well. So if you look at this location of CMT, as I told, it is in Bangalore. So that is the main center. Then we have another unit in Rajkot, Gujarat also. So these are the only two institutes of CMTA in India. So if you look at in Rajkot, Gujarat, it is a small unit for catering to meteorology service in and around that region. But main facility is already available in Bangalore, that is in Tumkur Road, Bangalore, near Yeshwanthpur basically. So though we are located in Bangalore, we try to serve across the nation. So reaching from top to bottom to east, west, and north to south, we cover almost everywhere. And also we try to serve other developing nations also. We help, for example, like Iran, Nigeria, Sri Lanka, Indonesia. So we try to develop such, we try to help those developing nations to establish center of excellence in manufacturing. So that is how we do. And so now we will come back to the core topic, that is additive manufacturing. So also you all, since it's all mechanical, so you'll be aware additive manufacturing. So the conventional manufacturing techniques, like if you look at the CNC machines or conventional machines, we generally start with a block of material, and if you want to make a final shape, you need to remove the material basically. So using a cutting tool, we remove unwanted material and then arrive at the final shape. So that is a conventional way of manufacturing in CNC route. So that is known as subtractive manufacturing. There are other technologies like forming technologies are there. You have casting, you have welding, like joining processes are there. So additive manufacturing, how it is different from those conventional manufacturing is that in additive manufacturing, essentially we add material layer by layer, by reading a CAD model, so that finally you have the three-dimensional physical part ready with you. So that means, in contrary to the conventional way of subtraction of material or joining of material, here we essentially add material to get the final shape. That is how we work in additive manufacturing process. So there are so many synonyms for additive manufacturing. If you look at in the early days, it was known as rapid prototyping. In the year 2000 and all, if you look at it, this technology was more popularly known as rapid prototyping, or RP technologies we call. So now if you look at it, this we can see the name called 3D printing very widely used. So that is one of the most buzzword we can say now, very popularly known as 3D printing. So there are so many other names also: additive fabrication, layered manufacturing, additive layer manufacturing, solid freeform fabrication, toolless manufacturing. Like that, you have so many synonyms. But to make it, but the international committee, the international bodies, they have given this name as additive manufacturing as the internationally accepted nomenclature for this class of technology. So if you look at the analogy from nature, how we can compare additive manufacturing to something that is already available in nature, you might have seen the honeybee hives, right? So honeybees, if you look at how they fabricate a hive, you can see all the honeybees have some sort of secretion. It's like a resin like or adhesive like material which will be secreted from the body of honeybees, which will be deposited onto some tree tops or rooftops. So over one day, it will be depositing one layer thick, so it will be a few thick, and on the second day it will be depositing on the first layer. Like that, over a span of several days, you can see the honeybees will be building its hive layer by layer. So after several days, you can see finally the honeybee hive. If you look at the shape, it is so complex that you cannot do this shape by CNC machine. The reason is that these honeybee hives have hexagonal pockets inside. So by CNC machine, you can probably machine the outside pockets to some extent, but inside pockets, they're all like a three-dimensional network of pockets. These things you cannot approach by a CNC route, because the tool cannot access inside pockets. But the nature has made it very simple, by this layer by layer approach, and make a complex shape which is not conventionally possible to make by machining process. So same technology, layer by layer addition of material, if you do in engineering domain, we can call as additive manufacturing. So basically, this technology is already existing in nature for thousands of years, because you can see if you look at any living organism, for example, human beings or animals or plants, any living organism, if you look at how they evolve, it is basically by addition of cells. For example, that is a building block, right? Cells. So cells forms into tissues. Tissues, when they combine, to become organ to organ systems and to a complete living organism. So similar way in additive manufacturing. So in engineering terms, if you talk for additive manufacturing, the additive manufacturing started coming into existence after the launch of CAD systems. That is the reason, if you look at in 1980s, additive manufacturing was commercially launched in the form of a process known as stereolithography process. That is the first type of additive manufacturing. So there are several types of additive manufacturing processes available globally, depending on what type of material you use, what type of energy source you use, what is the methodology you adopt for printing parts or additive manufacturing. There are different processes available. But if you look at all the different types of processes, there are certain steps in common. If you look at it, like for example, we start always from CAD model. So CAD model, you can either design a new CAD in a CAD software like SolidWorks or Inventor or Autodesk Fusion. So or you can have a reverse engineered data. For example, if you have an existing physical part, you can use a scanner to get the CAD model from that. That CAD model is the starting point for your additive manufacturing process. So once you have the CAD model, you will be slicing that data. The 3D CAD model will be slicing. That means you'll be dividing into different layers. Since it is a layer by layer manufacturing process, the first step is electronically using a software, you divide the CAD model into different layers. Then that layered information you send to the machine, additive manufacturing machine, where the machine will read each layer data, and then it adds the material to join the material layer by layer to form the final physical part. So these are the common steps, which are used in all the different types of additive manufacturing processes. So now let us understand. See, now you have different type of technologies available. So why we need to go for an additive manufacturing process? What are its advantages? Let us have an understanding. Then we'll go ahead with the different technologies. So one is to reduce the lead time in product development. Whenever you talk of NPD, new product development, one thing is, let us say the designer is designing a new part. So before launching into the market, you need to first make a prototype, and then you need to test its functionality, its aesthetics, and its performance you need to test. So when you want to make a prototype, you need to go for a manufacturing process. For example, if you are going, for example, if you take the example of a mobile phone or any other part, you need to, let us say, you need to go for a plastic injection mold. So injection molds, when you want to manufacture by CNC process, you have to wait, let us say, for few days or few weeks. If it is a highly complex part, large parts, then you need to wait for a couple of weeks also sometimes. So let us say in 2 weeks time we have made one tooling. So using that, you are making the product, or the prototype. Then you are testing it, and then you realize that you need to make some product changes. So again, for second iteration, you need to again make another prototype. So that will again take a couple of days to manufacture. Like that, design, if you look at it, it evolves by itself. So if, let us say, there are some 4 or 5 design iterations, then naturally it will take couple of months together to to bring the part from design to final stage. So but now competition is very high, right? There are a lot of companies now, so you need to, if you want to launch your product within short lead time into the market, then you need to have some technologies, manufacturing solution in which the prototypes or the parts can be fabricated quickly. So in this scenario of new product development, additive manufacturing is a very powerful tool. So the products which may take many weeks or many days to fabricate, you can make within a short lead time. So in additive manufacturing process, thereby you can reduce the time from design to market. So I will show you through some examples in the later slides with some of the industrial case studies, so that you can have a better understanding of that. So, and also you can, if you look at the products which are having complex features, complex geometry parts, if you have, the lead time will be again higher, so compared to simpler parts in conventional process. So, and so in such cases also additive manufacturing is very much handy when you talk of manufacturing a part with highly complex geometries. As you have seen the example of honeybee hive itself, that geometry is very, so whenever you have a highly complex job which is not easily manufacturable by any conventional process, you can manufacture that with ease in additive manufacturing. So you can see another example, tooling. For example, tooling industries, if you look at it in plastic injection molds, die casting, dies and all. So you can make that dies within a short lead time in additive manufacturing, so that we can start your production earlier itself. So then you have now a lot of research is going on new material development, and also you can think of parts which is made of multiple material. Generally in a given part will be having only one type of material. What if you have a new product which needs multiple materials in different regions of the product? So that also can be 3D printed by this process. Then you have unrivaled geometrical freedom of design. For example, initially so whenever you design any product, you need to think of how you'll manufacture also, right? So depending on the manufacturing process, you need to make the design changes accordingly, so that the part can be manufactured. We know about design for manufacturing assembly, right? So as you know, with every process there is some limitation. So for example, certain geometries you cannot manufacture by conventional process. So the designs which were impossible to manufacture is now possible with the use of additive manufacturing. So with examples I will show you. So because of that, the designers have higher design freedom, so that they can manufacture parts with higher performance with complex geometries which were impossible to make before. And you can see near 100% material utilization. So generally in conventional process, and as you know, it is a subtractive process. So you are removing material in the form of chips. So if you want one material, for example, one product you are developing, so 1 kg is the final weight. So initially the raw material weight may be around 8 to 10 kg. So the remaining 80 to 90% of the material has to be removed in the form of chips. So a lot of material wastage will happen. But in additive manufacturing, you are not removing any material, you're rather adding only the material that is required for the final application. So thereby the material utilization also can be, material is more effectively used with lesser wastage basically. And also it enables mass customization. For example, if you look at biomedical industries, so biomedical industries have a lot of customized parts. For example, implants, if you look at it, so implants will be highly customer specific or patient specific, we can say. You cannot have a single implant which will fit into everybody's body, right? So every patient will be having unique requirements. So if you want to customize for each and every implant, it will be more expensive in CNC route. Whereas in additive manufacturing, the beauty is that the different implants which is customized for each a patient, you can print in one go. So without any implication of cost. In conventional also it is possible, but it will be more time taking and expensive. Whereas in additive manufacturing, without implication of time, you can have different designs printed in one go. So with a lesser cost, that is the main advantage. So there is a famous there is a famous saying, a drawing is worth of 1,000 words. So if you want to explain a design to somebody, instead of expressing our words, you can show one drawing. So instead of, if you have a complex prototype again, instead of explaining through several drawings, you can show one prototype, so that will speak on its own. So to make such prototypes, this additive manufacturing is a very powerful tool. So there are different types of additive manufacturing systems available globally, depending on the material or its state. For example, you have systems, additive manufacturing systems that can make metal parts. You can make out of polymers or plastics. You can make out of ceramic like sand. Also, you can produce. And the raw material, generally in conventional subtractive manufacturing, always the raw material is in solid form, right? Solid billets we have. Whereas in additive manufacturing, the raw material could be in the form of liquid. Sometimes it could be in the form of powder. Sometimes it could be in the form of solid. Solid means it could be sheets, or it could be a wire or filament form. Like that, you can have different states of input material also possible in additive manufacturing system. Accordingly, you have different types of additive manufacturing processes. So, as per ASTM F42 committee, that is an international committee who works on the standards for additive manufacturing. So they have classified all the different types of additive manufacturing processes globally available into 7 fundamental processes. So these are the 7 types of additive manufacturing processes. So one is VAT photopolymerization, material extrusion, binder jetting, material jetting, sheet lamination, powder bed fusion, and direct transit deposition. These are the 7 types of additive manufacturing process. These are the international names. So if you look at a typical company's machine, they will call by different name. For example, stereolithography. So this is from a company known as 3D Systems in USA. They call SLA process. That is their trade name basically. Like that, you have solid ground curing. These are all, so bottom, whatever you are seeing, these are all trade names. For example, fused deposition modeling, FDM, that is from Stratasys USA, that is a trade name. Then like that, you have different names. And all these, these technologies are similar, and they can be classified under one of these 7 fundamental categories. So in today's session, so if you look at VAT photopolymerization, basically they are for making parts out of photopolymers, basically light sensitive material using laser. So this is photopolymer based. Then this material extrusion also is primarily for polymer parts. Like you have this ABS material, PLA materials. Like that, you have different materials. Then binder jetting is also mainly for uh, uh, polymer based materials. There are some technologies like X1, for example, for metal also, but with some binders and some post processing is required. And then material jetting is also mainly for photopolymers. Then sheet lamination also mainly used for polymer based sheets will be used. And so if you look at today's talk is mainly focused on metal additive manufacturing. So for metal additive manufacturing is concerned, the most prominent 2 technologies used are powder bed fusion and direct transit deposition. These are the 2 types of additive manufacturing process which is most widely used for metal additive manufacturing. These 2 are the technologies which I'll be focusing more today for the session. So you can see these different type of process and the different materials being used. For example, in steel lithography process, as I told, it is liquid epoxy resin. Light and sensitive material will be used, which is cured by using a UV laser. In fused deposition molding, the raw material is in filament form, which will be extruded through a heated extruder head to print the part layer by layer. In three-dimensional printing, you will be spreading a material, then you'll be dispensing a binder material to dispense. Then polyjet modeling, photopolymer. So you can see here all they're all mainly polymer-based materials. Whereas when you come to this SLS and DMLS, we can see from here onwards like selective laser sintering, direct metal laser sintering, electron beam melting, direct metal deposition, or laser engineered shipping. These technologies primarily they use metal powders. Especially in the last 2 technology, you can use either metal powder or wire as the raw material. So these technologies we'll be seeing in detail. So coming to the facilities at CMTI, so you can see, in fact, in CMTA, we were the first to install a metal 3D printer in India way back in 2000. So 25 years back, we have established our first metal 3D printer. Now, if you look at it, there are around 80 to 90 plus machines are available in India. That is powder bed fusion. So, later, those times only one type of material was able to be processed. Later in 2007, we upgraded our machine to process more number of materials. Later in 2011, we got our direct energy deposition DED technology, which was established in 2011, which is a 5-axis machine. So we'll see one by one. So the main objective of the center, additive manufacturing center at CMT, is to serve industries using this metal additive manufacturing solutions, helping the industries to accelerate their product development and also develop solutions using additive manufacturing for industrial applications. So along with offering services and solutions, we also develop machines as well. So if you look at now, we are focusing on developing customized additive manufacturing machines, which can be used by Indian industries. So we are trying to develop machines as well, and also we also try to disseminate this additive manufacturing technologies to industries through training programs, through such guest lectures, so to both industries as well as academic institutions. And coming to the facilities, as I told, one is powder bed fusion. We have that is laser-based DMLS process, direct material laser sintering. Then we have laser-based direct metal deposition DMD. These two are the metal-based additive manufacturing facilities available at CMTA. So we have another one, projection microstilography. So this was developed by CMTA itself. Basically, it is a projection-based 3D printing process, which can be used to produce a photopolymer-based micro parts, basically, which can have a feature size down to 5 microns also. So then we also have developed smart IoT-enabled 3D printer, which can be remotely controlled and monitored. Then smart foundry with 3D printer also CMTA have developed. So that has been developed and it has been deployed in National Institute of Advanced Manufacturing Technology, Ranchi. And so along with these developments, we of course have the related software for all these technologies, including Magix, Unigraphics. Then we have the Siemens DMD CAM software also we have. So coming to so now we will start with the powder bed fusion technology, that is direct metal laser sintering. So which I was telling, this is the this is the first metal 3D printer in India which is available at CMTA. So this is the machine and these are the subsystems around that. So if you look at the machine architecture, it is something like this. You can see there will be two platforms here. One platform will be filling with material. So here the raw material is in the form of powder. The powder of around 20 to 50 micron size will be filled onto this reservoir on the right side, and on left side you have a platform. It is a 250 by 250 size, XY size platform, which will be mounted here. So there will be two Z-axis motors. This can move up and down. So on top you have a laser source and there is a scanner. There is a galvo scanner with two mirrors. So what happens is there is a recorder arm. You can see this recorder arm or recorder blade. It will move to the rightmost end. Then you can see this is the sequence of operation. So the recorder arm moves to the rightmost end. Then the platform containing the raw material powder will rise up, and then the recorder arm will spread the metal powders onto the platform where we build the part. Then from top you have a laser which is controlled by a galvo scanner. This galvo scanner will control the XY movements of the laser beam, thereby focusing the beam onto the powder bed. So wherever the laser fall, there the metal powders will fuse completely to form a solid block. Then this will go down again by one layer thickness distance again. Then powder will be recoated. This cycles continue. So it will be recoating layer by layer and printing, and it is melted layer by layers. This is how the sequence of operation happens in powder bed fusion process. So now looking at the applications, so you can see here mainly this additive, this powder bed fusion. So if you look at, there are different technologies available. This is using laser. Sometimes instead of laser, you can use the electron beam also. So there, instead of laser, we'll be using electron beam to melt the powders. So in electron beam, you can process only metals. Only conductive materials can be processed. In laser, you can process either metals or even polymers also can be processed. And laser will have high resolution and with better accuracy, and surface finish will be better in laser-based process. Whereas in electron beam, the process, the surface finish will be little poor and resolution will be lesser when compared to laser, but productivity will be higher. So electron beam based. So that is very much used for biomedical applications, electron beam processes are used. But for other applications like aerospace, defense, and all, laser-based technologies are more widely used now. So yeah, so one is that applications, if you look at it, one is for making the metal parts. It could be for functional tests or for checking the form and fit, or it could be for end applications also. So now many additive manufacturing parts are flying components are also there, especially for aerospace applications. It is not only for prototype purpose. The end parts, the final parts which can be used for final application also can be produced by this process. Then you can also make use of this technology for making dies and molds for plastic injection molds, die casting, investment casting, rubber mold, metal stamps, stamping dies and all you can make. For such applications also you can use. Then special applications, for example, if you have a a mold with a conformal cooling channel, for example, which is not, if you have a cooling channel which is not straight inside, you can make use of this technology. I will show with some examples. Then also, if you have any component with highly complex structures like lattice structures, for example, for aerospace applications, you need to have a high strength to light, a high strength to weight ratio materials. That means you should have a lesser weight, but strength should be high. So for such parts, you need to have special structures like honeycomb structures or lattice structures. You can have gyro structures for heat exchangers and all. For such structures are very difficult to manufacture by conventional process, but very much possible by additive manufacturing. And also, if it is a bionic structure, for example, there are some structures. Bionic engineering, you may be aware, it is like mimicking the nature. So in nature, there are many structures which are very unique with high strength, but the structures are very complex. If you want to adopt that structure to engineering application, you will find it very difficult to manufacture because of the geometry, because of the complexity in geometry. But in additive manufacturing, since it is a layer by layer process, the such complex shapes also can be manufactured easily by this process. With examples, I will show you further. Then new materials also can be processed. For example, metal matrix composites, new types of alloys we can make. So, metal matrix composites, if you think, for example, if you want to make, it will be very difficult to machine by conventional process if you have a ceramic, part within that. So that will lead to high wear, of tools and all. So, but in additive manufacturing, since in this process you have a non-contact tool, that is laser, which can be used to melt the materials. So that way you can make, new types of alloys also can be manufactured. Metal matrix composites can be manufactured. So with this, I will take you to, these are the different applications. Now I will give you case studies, typical industrial applications, what we have worked at CMTA. You can see this is a 1:30 scale down model of a LCA aircraft. So this is around 500 long part, which, so in our machine, we have limitation of 250 by 250 So we split the part into three, and then we have 3D printed and then assembled to make this 500 long part. So this is a 1:30 scale down model, which was used for wind tunnel testing. So it took around 100 hours to realize this part by 3D printing process. The same thing we fabricated through conventional process also. It took more than 1.5 months. So that 1.5 months by conventional route has been reduced to 100 hours by this additive manufacturing route. So you can see another example for an automotive part, locomotive part, basically. So this is a part which was, printed. Just you can see the geometry. It has got some thread, and then you have some two branches. So this took only 20 hours to manufacture by this process. The same thing, if you want to manufacture by conventional process, you can think you may have to split the part into multiple, and then you have to fabricate the individual parts and then assemble. So here it was manufactured in one go. And then you can see another for governor body. So this is a this is a plastic part which has to be injection molded from this core and cavity. This core and cavity was printed in one go. Within 5 hours it was fabricated. Likewise, you have several examples, from, if you want, forming die, for example, this copper foil coil, it was transformed from one shape to another using this die. This die was manufactured by this process within 8 hours. You can see bevel gears, for example. This is for a bevel gear for an instrument, basically. So this will be injection molded from this core and cavity, what you are seeing on the top. This was fabricated in one go using this 3D printing process within 3 hours. You can see some more examples with steel. So previous molds were made of a bronze nickel based material. So this is a tooling steel. Basically, it is a H20 tool steel. Using that for electronic industry, it was fabricated. You can see several examples of impellers. It could be a 4-axis or 5-axis components also you can manufacture. And you can see one more beauty of this process is that even if you have multiple components, for example, you can see 6 different parts. This all the parts at once can be 3D printed in one go. So here you have a 250 by 250 platform. So here you can arrange all the different components. If you have still smaller parts, you can arrange in the remaining space. So in one go, all the different parts will be printed. So within 16 hours, all the 6 different components were printed. You can see 4 or 5-axis components also can be printed within a short lead time, around 2 hours 20 minutes. This symbol was printed. You can see complex honeycomb. This is an orifice plate. It is basically for nuclear application for IG car Kalpakam. So this is a honeycomb shaped orifice plate to control liquid sodium. So this shape, you can see honeycomb shape. At the bottom it is flat, on top you have a curved face on the top. So this was quite difficult to manufacture by conventional process, which was printed within 9 hours using steel in this process. Like that, you can have different types of mounting brackets for aerospace applications we have printed. You can see another interesting application. This is a roller in a ball bearing retainer ring, basically for plastic. For one of the industry, they wanted to make a retainer ring for ball bearings. Retainer ring has to be made by plastic. For making that plastic retainer ring, they need to make one mold. So this is the metallic mold. So if you look at that, inside the CAD geometry, you can see there is an undercut here at the bottom. So by CNC, probably you can easily machine the top surface, but at the bottom, it will be difficult to manufacture because of the undercut here. But here, so if you want to manufacture by conventional route, at least you have to split into 2 halves. But here, without splitting, as a single part, it was fabricated within 4 hours time using steel material. So another example of conformal cooling channel, if you look at the plastic injection molds, so as you know, in plastic injection molding, you'll be pouring molten polymer into the mold. So for cooling that, there will be cooling channels present. So cooling channels generally, if you do by CNC machine, it will be straight. So you cannot make a curved cooling channel, right? By if you want to do a machining process, you cannot make a curved hole inside, right? But you can see one example. This is for example, this is a hemispherical or spherical part. So this is so if you want to have if there is a hemispherical surface, if you want to make a cooling channel, you cannot make a curved hole like this in a CNC machine, right? So you need to make a straight hole, and then you need to cool it. So when you make a straight hole, you can see when it is straight, at some distance, at some areas, the cooling channel will be very close to the surface where you need cooling. In some areas, it will be far off. So wherever it is nearer, there the molten polymer will solidify very fast. Wherever it is away, it will take more time. Because of this differential cooling, the cycle time for cooling will be higher, and because of the differential cooling, the thermal because of the differential thermal thermal process, there will be defects which may form in the part as well. So here what we did is we have made a conformal cooling channel. It is like a spiral cooling channel. You can see this is like an Archimedean spiral. So here so when you pass a coolant through this, the coolant will be at it will be equidistant from the surface. So that means the cooling channel is conforming to the shape of the final part. That is why it is called conformal cooling channel. This type of channels you cannot do by CNC machining. So, but here it is very much possible. As you print, you can introduce the shapes which will be conforming to the final shape. Thereby, the advantage is that you will have a uniform cooling throughout. The cycle time for cooling also will reduce. So if you think of production, if you can reduce around 40%. There are many case studies which says around 40 to 50% reduction in cooling cycle. If you save time in production, it is like your productivity will come up. So for such applications also, this is a very powerful tool. So then you can see examples of heat exchangers. For example, if you have a complex heat exchanger part, which is very For example, you can see this type of heat exchanger. If you want to make, you have a lot of fins, and you have cooling tubes which is bent, and then it'll be. So if you want to make by conventional process, you need to bend the tubes, and then you have to do welding. The fins has to be welded. A lot of processes are involved. But here in this additive manufacturing process, what we did is we have printed the whole heat exchanger in one go. So as in a single go, it was printed. So no need to do any post welding. So directly the fins will be already, it will be integrated with the part as such. And also the cycle time also, it's within 22 hours it was printed. And the efficiency of cooling also can be enhanced. For example, inside, if you want to introduce some turbulators, you can introduce that, which is not possible in conventional process. Or you can have a different design of heat exchanger, wherein you can have a guy rod structures inside, thereby enhancing. So you can have higher area of higher surface area for higher dissipation of heat. So efficiency, the thermal efficiency also can be enhanced. So like that, you can have compact heat exchangers possible with lesser cost and time. Then you can see another example of a diesel particulate filter. This is an example where you have this honeycomb structures here. So here, if you look at the shape, it is not straight honeycomb. It is like, if you see the cross section, you can see it is inclined basically. So you have three different angles are there in within this design. So if it was a straight cut, we could have done by die sinking or wire radium, we could have done. But it is having a angle. The angle is not. It is not straight. The angle is also changing at least twice within the geometry. This was quite difficult to do, by almost impossible by conventional machining route. So this was made by this 3D printing route. Within 10 hours it was printed for automotive applications. So coming to next, so that is about the industrial examples for application examples for powder bed fusion process. So next, most popular metal 3D printing technique is direct metal deposition, so DMD. So this is a machine at CMTA. It is a 5-axis machine. And so here, what we primarily do is we have a laser which will be delivered through a nozzle. Through the same head, you will be delivering the material. You can either deliver a powder or wire through this head, and then the inert gas like argon gas will also be fed through the same nozzle. So the laser will be focused onto the area where you need deposition. When the laser focuses, there it will form a molten pool. So to the molten pool, the metal powders or wire will be fed, so that also gets melted, and this whole head will move in 5 axes. So you can have 3 linear axes like X, Y, Z, and you can have 2 rotary axes. So you can see there are so that means here in DMD you have a energy, you have a head with an energy source like laser or electron beam, or even it could be electric arc, or it could be plasma also. Different heat sources could be used. In this machine we are using laser basically. So then to monitor the process, you will have sensors like CCD cameras will be there. So these cameras will be looking at the melt pool to monitor the layer thickness uniformly, or to look or you can have pyrometer to measure the temperature and to control the process. So with this machine, you have 1 kilowatt laser. Basically, the part size is around 300 by 300 by 300. Actually, all XYZ 300. You can process most of the materials like different type of tool steel, stainless steels, Inconel, titanium like materials also can be processed. So coming to applications, in addition to conformal cooling channel printing, you can also do coatings also. For example, if you have an existing part, you want to coat upon that. Coating, if you want to do, coating is not possible to be done in the previous process. That is, in powder bed fusion process, the DMLS process, we cannot do coating. Especially when you have a 5-axis 3D surface, if you cannot do coating by powder bed fusion, because there you are spreading the powder layer by layer. But here we are not spreading. Instead, we are injecting the metal, the powder or wire onto the surface. Since it has got a 5-axis capability, you can do coatings on existing surface. You can do repair also, or remanufacturing of expensive parts you can do. Then you can have special applications like bimetallic parts. That means multi-material components. If you want to 3D print, you can do that. Functionally graded materials you can do. Like that, you can have special applications. The multi-material 3D printing is very much feasible in this DMD process, direct metal deposition process. I will explain with some examples. You can see some industrial examples. So this is a pump part which was used for aerospace application for ADA. So here we have to join the steel on top to the bronze on the bottom. So these two different materials are having different properties, different thermal expansion coefficient, different melting point, so different specific heat. So especially when you have two different materials having different properties, it's difficult to join. Generally we use friction stir welding like processes for joining, but there you cannot ensure uniform bond throughout the surface. So that was a challenge which was faced, and we could successfully develop a technology wherein we can deposit this steel onto the bronze base, so that we are able to get good interfacial bonding between the two different materials. And finally you can see this is the bimetallic pump part, axle piston pump made for aerospace application. So similar way we have done the reverse combination also. In the previous case we deposited steel to bronze. Here we deposited bronze to steel. So the reverse combination also was done, and we have done extensive characterization in terms of microstructure, micro hardness, then bond studies we did. So to ensure there is a good bond between the different materials. And also we did coatings also we have done for various applications. So you can see whenever you do a coating, so you can see this is the micro hardness variation from deposition to substrate. So if the deposition quality is good, then you need to have a gradual transition. If the deposition quality is not good, you can see on the right side it will be like a rapid transition in micro hardness, so there it may fail. So here we are able to establish a gradual transition in ensuring that the bonding is good between the coating as well as the substrate. So we did microstructural characterization, grain size analysis, how with the process parameter variation, how the grain varies also we have studied. And this is another example which we did for VSSC, for space applications. Here we coated one special type of material called co-nickel, cobalt, nickel, chromium, aluminum, yttrium alloy. It is a high entropy alloy. This material, we coated into cobalt based substrate like stellate material we coated. And conventionally they do through a plasma spray technique. So here we did through DMD process, direct metal deposition, and then we compared how the life of this plasma sprayed coatings and DMD sprayed coatings we DMD coated coatings we compared. And it was tested for oxidation resistance, scratch resistance up to 1200 degrees Celsius. And it was proven that the DMD coated coatings had higher life when compared to the conventional plasma sprayed coating technique. This we did for nuclear application along with IIT Madras we did. This is a Colmanoy coating on SS316LN, again for wear resistant coating. It is even up to 600 degrees Celsius it is able to retain its hardness without much wear. So this is also another example where we can use this DMD for coating applications. So this is for remanufacturing application. This is an example where this is a turbocharger shaft used in automotive applications, which will be rotating at a very high RPM. So there is a groove here. So the groove will wear out after some hours of operation. So here initially when the customer tried with the welding process, it was failing because the welding is causing a lot of distortion in the part. Here with controlled heat we are able to do deposition by laser, and then it was machined back to the design value. Thereby we are able to recover that shafts at very less cost when compared to original cost of the new part. So here is another example for aerospace application. This we did for HAL engine division, wherein there is a pump drive shaft. So here in the two shoulder areas it will be wearing out by around 0.5 mm. So here again by coating by like hard chrome plating was initially carried out, which was delaminating basically. So when we are rotating this a rotary part, so when if you do coating by hard chrome like electroplating technique, it was peeling off. By DMD we deposited on the shoulders, and then again it was machined by grinding. So after that when we tested at different conditions, there was no peeling off and it was satisfactorily performing in the test rig set HAL. So like that, you can have, turbine, for example, in aerospace, turbine tip, if you want to repair, you can do the repair through this process, so that you can say, so instead of throwing away the complete engineering part, you can do the deposition so that you can recover the part, minimizing the material wastage, energy, time and cost. You can save a lot. That helps in green manufacturing. So likewise, we have done for other industries also, for recover many fixtures. This is a fixture for which we did for Kirloskar Industries, using steel-based industries like that. Oscillating shaft, remanufacturing we have done. Instead of throwing away the complete component, we are able to recover the part by coating and then machining. So it is like a hybrid approach. You can do the material addition by 3D printing process, and then you do the finishing by machining process. So if you look at the material options, there are many material options available in powder bed fusion technologies. Different type of stainless steels are available, like 316L. We have 15.5 pH, 17.4 maraging steels, especially for tooling applications. Then you have titanium alloy, pure titanium also is there, and then you have Ti 64 alloys for aerospace, and medical grades are available. Inconel super alloys are there, like Inconel 625, 718, Hest alloys, cobalt chrome, aluminum alloys. Like that, you have different. Even there are some special machines available for processing precious metals like gold, silver, platinum alloy. 3D printing also can be done, but for that you need a specialized machine, because you need to have a good material recovery also. So there are machines available for that as well, available. And then we have directed energy deposition, DMD. So here also, we more or less, most of the materials used there also can be used here, with some refractory materials, like high melting point material also can be used here in the DED process. So now let us understand, when we have to. So now, provided we have a we have conventional process, you have a choice of many manufacturing process. So when you should go for additive manufacturing, when you should not go for additive manufacturing, let us have an understanding. So I will explain with an example here. You can see there is a you can see here, this is a simple part. It is a rectangular block. So if you want to make this rectangular block, you can do by 3D printing, or you can do by conventional milling. So 3D printing machine, if you want to make such a big, let us say, a solid block, you need to have so much material has to be added layer by layer. So it will be, especially when you talk of metal 3D printing, it will be very, very expensive for you if you want to make a solid block. But instead, you take a raw material block and take it to a milling machine. You don't need even CNC. You can have a conventional milling machine. So by paying few hundreds of rupees, you can get it manufactured very easily. So, but let us say, into the in the solid block, you have some special feature. For example, you have an elliptical projection in one side. Ellipse, when you have in conventional process, it is very difficult to control manually. The symmetry you cannot maintain. So naturally, you need to go for a CNC milling machine. So CNC milling machine is obviously more expensive than conventional milling. So that the cost of manufacturing goes up. Again, let us say, in the same geometry, you are adding some more features, like you have a deep rectangular slots to that with the high aspect ratio. Then beyond some aspect ratio in milling also, it becomes difficult. So you need to go for a EDM process, like die sink, for example. So for a die sink EDM, you need to make a tool first in another CNC, then you have to die sink it. So that means, as the design complexity or the complexity of the part increases, the machine's complexity also increases, and thereby the cost also increases. Now you can see this chart, wherein x-axis is the part complexity, y-axis is the cost per part. So if you look at the conventional or traditional manufacturing method, if the part complexity increases, the cost of manufacturing per part also, increases exponentially. Whereas in additive manufacturing, you can see the line is almost constant for very simple parts, like, as I told before, like block like materials. So the additive manufacturing will be too expensive. For very simple parts, additive manufacturing will become expensive, whereas conventional manufacturing is less expensive, more economical. But you can see, when the complexity of the design increases beyond a level of beyond a break-even point, you can clearly see that the conventional manufacturing becomes very much expensive for you, because you need 5-axis machine. You need to go for multiple machines, like combination of milling machine, EDM. So the cost will increase. Whereas in additive manufacturing, beyond a level of complexity, additive manufacturing becomes more economical, because when you have more and more features, you have lesser material to be added. That means, if you want to, if a designer has to manufacture a component which is highly complex in shape, then he need to pay high if he uses a traditional manufacturing route like CNC. Whereas in additive manufacturing, he need not pay extra, because there the machine doesn't know whether it is complex or simple. It layer by layer it splits the part and then it manufactured. That means especially for a complex part, additive manufacturing becomes more economical. Those are the ideal components. So for that means whenever you have a highly complex part which is very expensive to manufacture by CNC, then those parts will be the right candidates for manufacturing by additive manufacturing. So I will explain with some examples. There is a concept called DFMA, right? Design for manufacturing and assembly. Like that, to get the maximum benefit out of additive manufacturing, there are some design guidelines that is called DFAM, design for additive manufacturing. So you can, I will show you some of the with some examples so that you can appreciate, you can understand better. You can see this is a satellite component. This is the original design. Around 1.6 kg is the. It's basically like a sheet metal work. You can see there are several sheets and lot of rivets are there here. This is the conventional design. So to make it lightweight, so topology optimization, generative design softwares are available now. So topology optimized design is like this. So here you have several parts, several sheet metal components, so many rivets are there, assembly is involved, but the shape, the satellite component is redesigned as a single part. This is a redesigned antenna bracket. You can see the weight has been reduced from 1.6 kg to 940 grams. But this type of shape is very difficult to do by conventional process. But in additive manufacturing, we can easily produce these shapes. So the weight has been reduced, and the number of parts for assembly has also been reduced here. You can see another example of Airbus, part. This is the conventionally, made part. So you can see there are several components here. You can see there are 4 parts and 44 rivets are there. So this has been topologically optimized to make a single part. So the specialty is that the weight became 35% less here, and it's more 40% more stiffer than the previous part. So what is the benefit out of it? You can see when the weight is lesser, the fuel consumption of the aircraft also comes down. So thereby, over the whole lifespan of an aircraft, you would have saved so much gallons of aviation fuel. So even if you pay a little higher for this manufacturing, in case you'll be getting benefits down the line by saving on the fuels. So that is the reason aerospace companies are very much interested in this additive manufacturing process, because there the volume is less. It is not in huge numbers. So few hundreds or tens of parts only you need to manufacture. For that, additive manufacturing becomes very much economical. You can see another example of a Airbus A320 hinge bracket. So this is the conventionally designed part, which was done by investment casting. So this is redesigned by AM process. You can see it is made into still lighter than, so 25% lighter in weight by this titanium. It is basically a titanium part. So the weight was reduced by 40% basically. So thereby you have better benefits in terms of that means it is a truly, you can make a high strength to weight components with a high buy to fly ratio. There is something called as high buy to fly ratio. I think you may be aware in aerospace. For example, if you want to make one example I will tell you. So you can see here, this is a part, it is a gooseneck bracket. So this part, if you want to manufacture by your conventional conventional route, of course this design is quite difficult. The conventional design will be something else. But if you look at the weight of the part, initially let us say you have taken 17 kg of this block. After machining, the final component will be 1.5 kg only. That means remaining so much material is getting wasted. That is called high buy to fly ratio. How much you are buying the material, finally how much it is flying, how much weight it is flying. That is called high buy to fly ratio. For such components, additive manufacturing is very much beneficial, because instead of removing that 80 to 90% of material, you're adding only that 10% which is just required. So this is and added to that, you can build highly complex geometries. And so this is another example for seat buckle used in aircrafts. You can see this is the conventional seat buckle you might have seen. So this is a redesigned part through additive. So thereby reducing weight. And if you have so many seed belts, so seed buckles, if you have some reduction in weight every buckle, you will have a few kg reduction in weight. So similar way, this is a classical example from GE, General Electric's deep engine fuel nozzle. So this is the fuel nozzle which was made for for aircrafts. So in LEAP engines of GE, the original conventional design have 20 different parts basically. So 20 different parts used to be manufactured separately, and then each one will be assembled, and then it will be used in the final application. Whereas here, what they did is, instead of making the part out of 20 different parts, the complete part was redesigned as a single part. That means instead of 20 parts, it is redesigned into a single part, so that the inventory is reduced to a great extent. And then the cost also reduced. The manufacturing cost also was reduced by 30%. Weight also reduced by 25%, and it is more durable than the conventionally manufactured part. So in Cincinnati, US, they have GE have 300 plus machines which is in production for aerospace, and it is a flight it is a airworthy part. That means flight certified part example. So then you have other examples of Airbus A350s. This is the part this is the conventional design. You can see conventional part, it has got several parts which has to be manufactured and assembled. Now it is redesigned with minimum parts, and these shafts can be printed in one go in a platform. You can have all the different the shafts is printed in one platform, you can see here. So it is 45% less weight when compared to the conventional part, and the production cost also reduced by 25%, and number of parts also reduced from 10 to a single part. So that is how you can see the benefit from additive process. And this is another example of a monolithic thrust chamber. You can see this is a part wherein within the wall, to make it lightweight, lot of lattice structure is made. So this type of lattice structures you cannot machine within the wall. So when you print the part, you can make it with a lattice structures, thereby it becomes very lightweight but very strong. And also, if you have any cooling channels inside, you will have more efficient cooling because of the higher thermal management here. So like that, you can have several examples. So this is a biomedical part, hip implant. You can see it is highly complex. You can see it is a customer specific, a patient specific implant. It is quite difficult to manufacture by CNC, and very much possible by additive manufacturing process. So then you can see conformal cooling channel, as I told example of on hemispherical part, conformal cooling channel. You can have different conformal cooling channel for plastic injection molds, wherein you have this conformal the channels which is non-straight or non-planar cooling channel can be introduced for better efficient cooling. And you have this is an example of rocker arm design from Renault truck. This is the conventional design on the left side, and on the right side it is a topologically optimized part. So because of this additive manufacturing process, they were able to reduce the weight by 25%, and number of parts also got reduced by 200 fewer parts only they have to use. And durability also has been tested after the 3D printed parts being introduced there. And there are so many examples like that. You can see Mercedes-Benz trucks. So especially when you have a limited edition automobiles, instead of stocking the spare in huge number, you can have a digital library of your spare. So whenever on demand basis, you can take the CAD model and 3D print and supply it. So that way we can make spare part supply also you can do. And you can see design you can see some example. So let us say you have two channels combining into a single tube, two fluids combining into a single one. If you want to make this, let us say the loading conditions from top and bottom. Either you can have a solid block which will be too heavy, or if it is for aerospace application, you can do the optimization wherein you can have lattice structures like this, which will be very lightweight and very strong also. These structures, it is very difficult to do by CNC route, but very much possible by additive manufacturing process. Like that, you can have different examples for aerospace applications or biomedical applications also you can have. And as I told in the beginning, for biomedical application, mass customization. This is an example wherein in a single platform, 461 different parts with the different designs is printed in one go. So in 22 hours 20 minutes, the whole the customized dental parts is made in one go. So it enables, that is how I was telling, so that it becomes more economical. Otherwise, you can think, if you want to make the same thing by CNC route, it will be very much difficult and time consuming, and it will become more expensive. Whereas for biomedical, this becomes very much economical, since we print the complete part in one go, enabling mass customization. So to conclude, so we can say in additive manufacturing, we can use this process for making complex parts, especially more economic. The complex parts can be made more economically. The shapes which are impossible to make by CNC also is possible by additive now. And not only single material components, you can make bimetallic parts also can be produced. You can make you can do remanufacturing of expensive engineering components like turbocharger shafts. You can remanufacture, helping in green manufacturing. Then you can also do hard facing, that means coating of corrosion resistant or wear resistant coatings. You can do conformal cooling channel with better efficiency. You can make in molds. You can make tooling within shorter lead time, and also metal matrix composites. You can make functionally graded materials. You can make. So that is about the different applications. To that I would like to add one more thing. So we are also working on a new machine. So now if you look at the machines available in India, most of the machines are imported. Powder bed machines, there are some companies who manufacture in India itself for DED process, which is very much beneficial for making bigger parts. There is no machine which has got indigenous subsistence within that. So as part of this, CMT is working on a new project that is for development of laser based directed energy deposition machine. So here we are partnering with an industry in Gujarat, and we are trying to develop the machine. So this is a wire fed laser based machine which can go up to 1 by 1 meter size also, and it has got a 5-axis capability, and all the subsystems, major subsystems, are developed within India itself. So that is about the product, this new machine. This machine is under development, so it will take another a couple of months to become ready. So first prototype we had displayed in the IMTEX exhibition in Bangalore International Exhibition Center, BAEC Bangalore. Last 2025 January month we displayed. This is the first version of the machine for non-reactive materials, and next version is coming up, so which will be ready in few months time. So with that, thank you all of you for your kind attention. So if you have any questions, you can ask now, and this is my contact detail. So if you have any requirement, so you can let me know and discuss. Thank you.
Thank you so much, sir, for your valuable session and time.
Sir,
Thank you. Yeah.
Participants are requested to ask your questions if you have any.
hello.
Hello.
Yes. Please
Yeah,
do.
sir, this is Dr.
Sir,
Srinivasan from
actually, I'm working in the aeronautical engineering department. Students were asking about that internship. So is that CMTA provided internship for the students, sir?
Yeah, we have some internship programs also. You can actually, if you visit our website, there is one, you can contact our training department.
Okay,
so there
sir.
is a center called AEAMT, Academy of Excellence in Advanced Manufacturing Technology. That is a center who coordinates this internship programs. If you
Okay, sir.
go to our website, you can go to our training. So you can send a mail to them. So they will guide you.
Yes, sir. AEAMT, right,
Yes,
sir?
yes.
Yes. Thank you, sir. Thanks so much.
Yes.
Hello.
Yes.
Yeah, sir, this is Dr. Srinivasan from SRM Valley Medical College, sir, Chennai.
Okay.
Sir, once we are going to reduce the material weight, then how we are going to compromise the strength properties during the applications?
So basically, I think you may be aware there is a software called softwares for topology optimization, right? So that means, see, for example, I was showing one example here. This part is in so for getting so you'll be having some loading condition, for example some 500 newton or 1000 newton force is coming. For that you need not have a solid block here. So for getting that same strength, for sustaining that, instead of having a bulky solid block, you can have a different design. So if you have this topologically optimized design, so without compromising the strength, you can reduce the weight. So that is what we do in in topology optimization technique. So thereby, so you will not be, you can give the boundary conditions. What is the strength you need? If you give, you can you can optimize the design. So it is not necessary always that you need to have a bulky material to be strong. So for given loading conditions, you can always redesign the part so that it becomes strong but lightweight. I have shown several examples before also in the slides wherein it can have higher strength.
Yes.
Good evening, sir.
Good evening. Yeah, please.
Yes, sir. I am from NIT Arunachal Pradesh.
Okay. Yes.
Yes, sir. My question is like in FDM, we have multi-jet printers, right, sir? If you
Multi-jet.
yes, multi-jet, like multiple injector will be there, sir.
Okay, for a small clarification, in the beginning of my presentation, I was showing the 7 different types of processes. So
Right.
in that, some of the processes I just explained for understanding purpose. But the facility wise, if you look at CMTA, we have powder, this metal based process like powder bed fusion and direct energy deposition. These are the, so there we can do multi material printing. We can do.
Okay, okay. So
Yes.
that is my question. So multi-material printing we can also do, right, sir?
Yes, it is possible because, for example, in DMD process, direct metal deposition, you have 2 material feeders. So you can have 2 different materials and then you can print. So you can program the way you want it to be printed. So multi-material printing is possible. Yeah.
Okay, thank you, sir.
Question in the chat box. How do you calculate DFM score, also DFA index?
Sorry.
How do you calculate DFM score, also DFA index?
So right now we have not worked on that those aspects. If you look at, there is one university in Gujarat. Are you, by any chance, are you working on this DFAM things?
Oh, there is a question on this. Question was in the chat box.
Okay. Basically, there is a university called PDEU, basically Pandit Deen Dayal Energy University. I think one of the projects they were doing for this same aspect. Right now, there is no ready-made solutions available. If you look at the software available for design for additive manufacturing, there are softwares like SumuFact Additive, or Altair, Inspire, like that. Some softwares are available. So if you give what is the type of additive manufacturing process and the boundary conditions, it can do the design for that. I mean, it can modify the design to suit for, because see, you let us in additive manufacturing, definitely you have higher degree of freedom, but it doesn't mean that it can print everything. Actually, this also has some limitations. So in the now, people are companies are working on how to feed the software to understand what is possible, what is not possible, so that a designer, when he gives a boundary condition, the design will be changed in such a way that it will be possible to manufacture by a given process.
Another question in the chat box. Can we visit CMTA and see those machines physically?
Yeah, you can. Yes.
Hello, sir.
Yeah.
Hello.
Yes.
I'm Manik Patil from BITS Pilani, Goa.
Okay.
Actually, I'm working in DED of Inconel 718, and I visited CMTI for measurement of the residual stress during the deposition, actually.
Okay.
So the residual stress values are very high in case of direct energy deposition. So is there any remedies for that?
Okay, so generally, see, it depends on, I don't know which process you did. You use laser-based technique or any other? Which process?
Yeah, laser-based only. Laser-based only.
Laser-based, actually.
Yeah.
So residual stress depends on various factors, basically. So it depends on how you clamp your components. What parameters you use, whether you use high power or high speed, or Like that, you have basically it is a thermal cyclic. I know, there'll be so many cycles. Thermal, it is like a heating, cooling, like that. So
Yes.
obviously stresses will be there. But if you want to really reduce that, you need to one thing is what you can look at is how you do the deposition. For example, the scanning pattern, the what way, if you're printing a part, in what scanning pattern you're following. For example, whether you're using a alternate XY scan pattern, or there are strategies like island pattern, chess pattern, or every layer you can rotate by 90 degree or 45 degree. So the scanning strategy also matters. And second thing is, you can do some cooling actually. For example, substrate preheating you can do to reduce the stresses in the part, or you can do post printing, you can do heat treatment also, you can do, thereby reducing the part. Or in situ, in situ treatment also you can do. For example, every layer you print and then do heating by laser. There are different techniques available for that.
Got it, sir. Thank you, sir.
Can I ask a question, please? Hello?
Hello? Yes,
Yes,
yes. Yeah.
Can you please put some light on DFAM?
Sorry?
Can
Yeah,
you?
DFAM. Basically, DFAM is a, basically it is a little vast topic, basically, DFAM. So right now, as I told, before how we were doing. So when we started working on this some couple of years back, there was no software tools available. So by experience, we'll be knowing what things it can print. For example, there is a concept called overhang features. Overhang, that means if you have a vertical, let us say you are building a T shape here, you cannot build the horizontal roof directly by 3D printing because there is no support below. This is called overhang. So what happens is, over a period of time, you'll be understanding like what is the, what are the angles. For example, instead of 90-degree turn, you need to give some angle here, self-supporting angles it is called, like 40-degree or 45-degree, depending on the material, layer thickness, and the process. You need to choose it. So now, for as far as design for additive manufacturing is concerned, every manufacturer, they will give some guidelines. Design guidelines will be provided. For example, in terms of what is the for example, if you are printing a thin wall of 1 mm thickness, what is the height to which you can build for a given material? It will be available. If it is a circular shape, if it is a long wall like structure, what will be the aspect ratio possible? So those certain things will be available basically in the guidelines from the machine manufacturer. As such, in software now, as I told, it is still evolving. There's no full-fledged software which we can say that is available, which is capable of doing DFAM. Currently, it is evolving. Now, more people are more relying on the experience, basically. So by undergoing, this process, by printing several parts, by learning different conditions, we need to apply the DFAM principles to that.
Another question is, can you tell something about ink-based direct writing technology?
Sorry?
Ink-based direct writing technology.
Okay. Basically, I think that comes under material jetting technology. Basically, material jetting
Right.
technology. So basically, if you look at that, there are some companies like Optomic US and all. So they are working closely with that type of technology, wherein they try to have conductive materials, conductive inks. For example, if you think of electronics industries, generally you have a PCB which is flat. But if you have on product, let us say mouse or some, you have some component which is not straight. If you want to have a circuit that is conforming to the shape, using a 5-axis machine, you can basically draw one circuit, electric circuit you can draw using this technique. There are techniques like aerosol jet printing is available, wherein they use a conductive ink to write directly, conductive materials like copper infused materials are available, or silver infused materials are available, wherein we can 3D print the part, so that you need not have soldering into that. Directly you can write the circuits onto non-planar surfaces. And that is one thing. Another thing is for biomedical applications also. For example, there is something called as bio 3D printing. So there they use some special fluid media to print cells itself. For example, if you are developing a new type of drug, if you want to check how the cells will be reacting to that new type of drug, so you can rather have that stem cells you can print that to form some tissue assembly, and then you can have the drug. So instead of testing on animals initially, you can test on this stem cells, which is 3D printed to form. So there also we use some type of inks that is like bio 3D printing applications. Then another thing is food 3D printing is also another area where people are doing research, where people try to form certain formulations wherein we can 3D print food directly.
Thank you, sir. Thank you so much
Thank you.
for your
Thank you very
valuable
much.
session. Thank you, sir, for your valuable session and time. I hope there are no more questions, so we shall wind up the session and we'll meet tomorrow.
Okay. Thank you,
Yeah,
sir. To conclude today's session, so I invite Mr. Dr. Rohan Xavier to deliver the vote of thanks.
Good evening, everyone. On behalf of Bethlahem Institute of Engineering, I am honored to deliver the vote of thanks. First, I would like to thank our chairman, Dr. Gerald Silvaraja and Professor William Dharmaraja for making this event happen. And I would like to extend my thanks to our patron, Director Engineer T. Aisen, Principal Nirmal Singh Sir, Gerald Jabakumar Sir, our Dean, and our Dean Academics, Dr. Crispin Das. And I would like to thank our HOD, Mr. Jabdru, for arranging this type of faculty development program. And I would like to express my deepest gratitude to our resource person, Mr. Vinod AR, Head Additive Manufacturing Group, Central Manufacturing Technology Institute, Bangalore. Thank you for the insightful session on metal additive manufacturing for industrial application. Your practical examples and industry perspective gave participants a clear view of production scale AM. Thank you, sir. I also thank all the participants and faculty who joined in this evening to make this session lively and meaningful. Thank you all. Thank you for attending the program. Thank you.
Yes, sir.
thank you.
Thank you, sir.
Thank you. Yeah.
Can we get the recording of the session, please?
So we can share in the WhatsApp group, sir.
I'm sorry?
Sir, we will share in the WhatsApp group. Okay, sir.
Okay, WhatsApp group पर link भेजेंगे, right? PPTs also?
Okay, sir. Possibly we can share, sir. Okay, sir.
No, thank you.
Okay, sir.